So our last question is another one that's straight off the AP Stats exam. This is actually what they call an investigative task from last year. And the investigative task is something I really love because it's a question where you have all the tools to be able to solve the question, but at no point during the course should you have actually done this question because it's something completely and utterly new, and you have to put your tools together to figure out how to do it. So let's go ahead and tackle this question together, seeing what the heck we've been given. So if you want, by the way, feel free. The first couple of sections are straightforward, and that's when the wheels sort of fall off. But this is like, if you could do this, you should be able to get like 100% on an exam. So systolic blood pressure is the amount of pressure, blah, 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 blah. The mean systolic blood pressure for people in the U.S. is reported to be 122 with a standard deviation of 15. In fact, the fact that they mentioned the entire U.S. and there's nothing here to say it's an estimate is leading me to believe that this is the real deal mu and the real deal standard deviation. The wellness department of a large corporation is investigating whether the mean for its employees is greater. Okay, we got a direction. We're probably going to be doing some sort of hypothesis testing, right? Than the reported national mean. A random sample of 100 employees, there's our N, will be selected, and the systolic blood pressure for each employee in the sample will be measured, and the sample mean will be calculated. So they're going to give us a sample mean, but they haven't given it to us yet. And again, if we wanted to kind of think about this, we've got systolic blood pressure as our variable, which is quantitative. So mu represents the mean for all employees. Consider the hypotheses. All right, this makes sense, right? We had seen that already. We saw the greater than. We were ahead of the game here. So we want to know, is all employees different than all people in the U.S.? So our first question here asks us to describe a type 2 error in context. So remember, a type 2 error is when we fail to reject the null, but the null is actually false. Or we can think of it as when the truth is the second one, but we decide this. So type 2 error in this context is that we're going to decide to fail to reject the null, right? We're going to say there's not enough evidence to show it's higher, but it really is higher. So there isn't evidence, I guess it's not we, it's the wellness department, but whatever. There isn't evidence to conclude it's higher. And I'll be lazy, systolic blood pressure is higher when it actually is. Which could be an actual issue here, right? Because they're going to basically think they don't have an issue going on. They might not do some sort of wellness program when they really should have been doing some sort of wellness program because their employees had high blood pressure. So, all right. Part B. That wasn't so bad. Assume that sigma, the standard deviation of the systolic blood pressure of all employees, is 15. So before we had sigma for everyone in the U.S., but now they're saying that this is actually sigma for all employees. They're letting us know that we have sigma, so that way we can use a z as opposed to a t. If mu is equal to 122, the sampling distribution for x bar, the sample level, is approximately normal with it. Okay, they're telling us everything we know from 7.1. They're saying the sample mean, if n is equal to 100, is approximately normal with a mean of 122. And remember, we could have grabbed this from the formula sheet. The mean of x bar is the real mean, which they told us. This is assuming the null hypothesis, right? And the standard deviation would be the original standard deviation divided by the square root of n. And oh, they did that for us. This is like making it so we can't screw up. So I'm going to tell you right now, this question was the question that got the most zeros on the AP ever, I think, for an investigative task. Like a lot of students just left it blank. And hopefully right now you're going, they should have at least gotten the point from doing part A and part B. But we'll see how this keeps going. What values of the sample mean would represent sufficient evidence to reject the null hypothesis at a significance level of significance level of 0.05? So essentially, this is like our rejection region problem, except for instead of asking for z's that would have us reject, they're asking for sample means. So I want you to take a moment and think about what the heck you might do here. I would draw a picture because you know me, I love a picture. I want to change this to red so it matches my approximately normal work. We know our approximate normal is centered at 122. We know we were doing a right-tailed test, right, from above. And we know what that means in terms of our alpha. If we're going to reject the null, that means this tail probability has to be less than 0.05. So we need to know what values of x bar would give us out a tail probability less than 0.05. And hopefully you're screaming at the computer that we have a calculator shortcut to do this, right? If I know the percentage and I'm looking for the cutoff, this is what inverse norm is for. We'd use the left side probability instead of 0.05. We'd want to use that 95%. We know the mean and standard deviation because they were nice enough to walk us through, so we didn't use 15. So let's see this thing. Second distributions. Second button distributions. Inverse norm 0.95, comma 122, comma the 1.5. Because we want sample means, not x's. So 124.47. So they asked us for values, right? Not just one value. And this is where we have to use the same work we were doing in the rejection region piece. Anything there or higher would have us rejecting the null. So let's just write out that in a sentence. It'll be easier. We would reject the null for x bar greater than 124.47 millimeters mercury. So if they take their sample of 100 employees and the x bar is this, we don't even need to finish the entire hypothesis test because we already know that that probability is going to be less than 0.05. Here's where this one gets tricky and where this becomes a true investigative task. Though we have never done the inverse norm for our p hat or x bar, it does make sense though. The actual mean systolic blood pressure for all employees is 125. So they're now giving us, the real deal mu. They gave us a bunch of keywords saying this is the real mu. That hypothesized value of 122 is incorrect. It should have been 125. And turns out the standard deviation was 15, so that was fine. So using the actual mean of 125 and the results from part B, determine the probability that the null hypothesis will be rejected. What? So using the actual mean of 125 and the results from part B, determine the probability of rejection. So probability means we're looking for an area under the curve, right? And we now know that the real mean, x bar is still normally distributed, but what was wrong in this previous example was this shouldn't have been 122. It should have been 125. And we know we're doing a normal CDF question because we're looking for a probability under this normal curve. The issue is just figuring out what the heck we're looking for in terms of what part of the curve are we talking about. And that's where this comes in. We would reject the null if x bar is greater than 124. And we want to know its probability of rejecting. So we're going to take that 124, and we said we would reject for any values greater than that. So we're going to do normal CDF of 124.47 up to E99 for a mean of 125 and a standard deviation of 1.5. That would be an easy mistake to make here, is forgetting that if we're doing this for sample means, right, we got to use that standard deviation for our sample mean. I needed to convert that to the standard deviation for x bar. So let's see what the probability is. Okay, do a normal CDF, 124.47, 125. Oh no, I need the E99. Drat it. E99. 125, comma 1.5. My goodness, I'm having a terrible day of typing on this calculator. So we get out 63.81. So just a quick little aside. We just figured out that there's a 64% chance that we reject the null, when it turns out we should actually be rejecting the null, right? Because the value was not 120. So what is the term for that? We just found this. What the heck did we just find? We just found the power, right? We rejected the null. There was a probability of rejecting the null when H naught was actually false, right? It needed to be rejected. We knew it was 125 and not 120. So that's exactly what power is. And then E says, suppose the size of the sample of employees to be selected is greater than 100. Would the probability of rejecting the null hypothesis be greater than, less than, or equal to the probability calculated in C? Explain your reasoning. So what happens as we increase our N? Just thinking really simply, we'd probably think if we increase our sample size, we're going to be more likely to reject the null because that's what we want, right? And as we increase sample size, good things happen, like power increasing. So that's a very basic way to say it. It's just we know, right, as you increase your sample size, your power will go up. But there is a classier way to explain this, and that classier explanation has to do with looking at these two normal distributions, because there are two, right? We have our normal distribution centered around our null value, centered at 122. And we have a distribution centered at the true value of 125, right? And so our rejection region for the 122 area ends up being the probability in this 125 land, right? Like, so here's the reality, here's what we're testing. So what the N is actually going to do here, if we increase our N, what's going to change is our standard deviation, right? That's going to get smaller. So this is going to transform, and we're going to have a narrower graph for the hypothesis test, and we're also going to have a narrower graph for our true distribution of what's really happening behind the scenes. So when we look at this rejection region, which, we still need 5%, so we're still going to be way over here. Now that's going to be a hell of a lot more of the curve for 125. So that decrease in standard deviation is actually impacting both our hypothesized distribution as well as our real distribution. So it is going to take the actual X bar, the necessary X bar for the rejection region is going to get pulled way closer to 122, which is also going to pull it way further away from the 125, resulting in a much larger probability there.